Uh, so yeah, I mean, this time, as we were discussing, like it will be the last time. I will just do a recap of like a very small recap of what we were trying to do. So we were going through motion estimation, and we talked about one approach for doing motion estimation, which is a classical method, but it's actually a very good method to go through because it inspires a lot of the research in even in deep learning based approaches for estimating optical flow. So the method we were discussing is, which is Lucas Canada, it actually relies on this local smoothness constraint. And we actually, let's go first that any optical flow method is relying on the assumption that there is a brightness constancy, what we call as brightness constancy assumption, that from frame 1 to frame 2, there is an assumption that like the pixel that you're trying to track will not change its intensity, which gets violated a lot, of course, because of local illumination changes and everything along that line. But we talked that it's a basic assumption that we start with to be able to estimate motion. And we talked about how we were able, through expanding the going through the Taylor expansion and deriving until we went through this equation, which is using the gradients in the x, gradients in the y, and UV are actually the estimated, like the optical flow and the flow direction in terms of in the x-axis and the y-axis. So optical flow is always like think of it as the apparent motion in 2D. We're not looking into 3D right now. And negative FT, where FT is the temporal gradient. So this is the equation that we built based on the brightness assumption. And then when we went to Lucas Canada specifically, we talked about the local smoothness constraint. So the local smoothness constraint is a way to help have multiple equations to be able to solve this linear system of equation with two unknowns. And we assumed that in a local neighborhood, let's say a 3x3, that the 3x3 pixels are going to move similarly. So that's what is called local smoothness. So in this case, we can use the 3x3 window. So we have 9 pixels. We can use the gradients, the x, y, and the temporal gradients to actually construct our linear system of equation. And we talked about how this is an overdetermined system. We have 2 unknowns, but then we have 9 equations, for example, if we're doing a 3x3 window. So we talked that generally, if you have an overdetermined system, you go for using in a linear, when you're trying to solve a linear system of equation, then you go for a linear least squares solution. And this is a hacky way of explaining it, but people actually want to know like why this normal equation gets the solution. I can share like 2 slides like talking about the geometric interpretation. I have used it before in other explanations, but I will not be able to go through it. It's too much. So I can share this slide with you. I was actually borrowing it from another presentation. Like it's talking about it's actually explaining it in a geometric way. And I love the geometric interpretation. But at the end, you will be able to see that in order to get the trying to estimate, in our case, it's the UV, like the optical flow, you can use this form of this normal equation. So in our case, back again, not to confuse you. So we had the A, where the A is this 9x2 matrix, and which is constructed from the image gradients spatially. And then we have the B, which is the vector of the temporal gradients. And then M for us is the vector for the UV that we are trying to estimate. So at the end, the solution will just be A transpose A inverse multiplied by A transpose B. And this will be how we are, this will be the way we are going to solve our optical flow. I'll just give me 1 moment. I need to get, yeah, now I have it. So yeah, and then I remember last time someone was commenting that what if we just did, like I have A m equal B, I can just say that M equal A inverse B. Well, the problem is that A is not necessarily invertible. So we go for this way of solving it, or doing a pseudo inverse. I think I'm honestly don't remember if, like, they're probably related, but I don't remember. But at the end, you cannot just do direct inverse. Like in very rare cases, when you're solving your linear system of equation, you will be you have the A invertible. Mostly, it is like most of the problems that I've worked on. It is not. It is not invertible when. Yeah, I mean, we don't want to go through the details of the linear algebra, but sometimes like you have some dependencies between the columns or the rows, then it becomes not like you cannot invert it. So this is why we go for this normal equation. So yeah, I mean, hopefully no one has any issue with how we constructed the A, the B, and how we will simply use this. I'm not explaining exactly how we derived it. Again, this is kind of hacky way of how I'm showing you here, but I'll send you the slides if you want to go through it outside of the session. But at the end, you see that A transpose A, we have, this is the X gradients, the Y gradients, and we just did a transpose for this matrix. So we have here 2 by 9 matrix and 9 by 2 matrix. If we multiply together, you end up having, if you go through this row multiplied by this column, this is basically taking fx11 by fx11 plus fx12 by fx12 and so on. So this is like doing a summation of the fx for all the pixels. Similarly, if you take this row multiplied by this column, it's now doing a summation where you're multiplying fy by fx. And if you take this row here and multiply by this column, so summation fy fx again. And lastly, like if you take this row multiplied by this column, we end up having summation fy fy. So we have this 2 by 2 matrix that we constructed by doing this A transpose A, which is oh, sorry. Yeah, which is this part here. So this part here, it's I hope it is clear. We just use the image gradients, and we will discuss even how to compute this gradients, and we'll go through the practical with the code. I think with the code things clear up always. So yeah, this is this is here the 2 by 2 matrix after doing A transpose A. And now this is the part where I'm going to do is the A transpose B. So if you remember A transpose B, so instead of, like, you can forget this part, I can now add the B. So B is the FT 11, FT 12, and so on, right? So if I take this matrix multiplied by this vector, you end up with this 2 by 1 vector here. So, which is basically taking the gradients in the X multiplied by the temporal gradients and the gradients in the Y multiplied by the temporal gradients. And we're always here summing over the pixels. And of course, we still have the negative sign from, this is from the original equation of the brightness assumption, the brightness constancy assumption, okay? So again, to make things in summary, what we did, we used linear least squares in order, so because we had more pixels, like we had 9 equations to solve for 2 unknowns, UV, and simply taking this 2 by 2 matrix here, and this 2 by then and this vector, we can use it to construct our UV, okay? So if we do an inversion for this, we can and multiply it by here, then we will be able, like if we do a pseudo inverse of this one, multiplied by this vector, we'll be able to get our final solution. And the last thing we discussed about is that it's actually better, or it results in a more accurate solution for optical flow when we are looking at corners. So if you remember, let me go back a little bit. Yeah, if you remember that if we, like the corner here, if we are like watching the corner, we'll be able to see the proper motion. That this is, for example, like going diagonal, where at the edges there might be some ambiguities. It also depends on the window size, by the way. So the window size can tell you whether ambiguity will occur or not, even on the edges. So yeah, I mean, all in all, like in most situations, it's better. That's what they call it, even good features to track, like these corners, because you avoid any ambiguity. Like, you know that it's going to move. If it's moving diagonally, you can identify it. So this is the other thing. And yeah, I mean, this is again like a summary of the algorithm. So if I want to do Lucas Canada, what I simply need to do is compute the image gradients in the X and the Y, compute the temporal gradients between the two frames. So we're always estimating motion. Optical flow is, again, like apparent 2D motion between two consecutive frames. So we can use that to compute the temporal gradients. Then we compute this matrix, this vector, and invert and multiply, and then we have our UV. Okay, so yeah, any questions actually on how the algorithm like proceeds with estimating the motion? Everything is good? Okay. Okay, so I'll tell you, before we proceed, what do you think? How can I compute image gradients? So for the ones that were there during the early sessions, we talked about it a bit. So what do you think? If I want to compute the gradients in the X direction and the Y direction, what can I do? Yeah, I mean, you can type in the chat if you want, or you can just open the speaker and so again, to just repeat the question, how can I compute the image gradients in the X direction or in the Y direction? Convolution, thank you, exactly, Omar. Convolution with what? So we're gonna do image filtering and convolve our image with. We took one type of filter that is doing gradients. Do you remember? Or
I don't remember the name, but yes, there is 3 or 4 filters who could do it diagonal or left or down, horizontally or vertically, but I don't remember the name. So
okay, thank you, Omar. But okay, so I'll tell you what. When we say gradients, so it means rate of change, right? The simplest, like we're trying.
0, 0, 1.
Yeah.
A
Okay.
column
So
with
0,
0.
1, then it's actually -1 and 1. You can do that, or like 1, -1. So for example, this is like trying to see the change across the X direction, or 1, -1. So like on the Y direction, like we're trying to see the change. You can average it over a 2 by 2. And Daniel, what you're saying is correct. So Sobel filter is like one way also. Like there are, again, exactly as Omar was saying, there are multiple filters that can be used. So the Sobel filter is also doing the same, but averaging it on a 3 by 3 patch and doing some smoothing. So like you can have here 1 to 1, and then -1 to -2, sorry, -1. So this will get you the vertical edges. So it will get the change in the X direction. So you see here, we're doing difference from the name gradients, like this is the rate of change, right? So from the, we're doing the rate of change, then we're trying to get 1 pixel minus the other in the X direction, forward or backward, or in the Y direction, up or above, sorry, up or below. It doesn't matter, but as long as we're capturing some change. And you can do it over a 2x2 patch. You can do it over a 3x3 patch and do some smoothing here, like give higher weight, like this 2 is giving higher weight to the center. All of these will still give you the gradients that you're looking for. And the direction is based on how, if you're trying to do here 1, -1, so this is taking the change in the y direction. If you're trying to do it, so let's say here, this is 1, and this is 1, this is -1, and this is -1. So we're doing the change in the x direction. We're differencing in the along the x. So this is the x direction. If you're trying to get the gradients, so this is also something to keep in mind. If I am here doing the gradients in the x, so this is fx. So fx will capture edges horizontally or vertically. What do you think? It always gets confusing, I know. So I'm trying to difference along this direction. This is the x direction. So this will be which type of edges it will capture. What do you think? You can type also in the chat. Would you is it gonna be a horizontal edge or a vertical edge? If you feel that this is an you want me to go through, it's okay, you can tell me, but yeah, I mean, even guess. So again, I'm doing 1, -1, so I'm trying to get the change along the x. So this will capture horizontal edges or vertical edges. Anyone wants to guess?
I think the upper one, which is 1 on the left, -1 on the right, this will detect the vertical edges because it's go horizontally. Then when there is a change between 2 pixels, it will draw the line vertically, and yes,
exactly. Yes, it will reinforce the vertical edges while this one is reinforcing the horizontal edges. So thank you. So at the end, like the gradient direction is perpendicular on the edge direction. Okay, so yeah, thank you. So this is again a recap of what we took before. So we just to here. So we are going to use this. So this is our kernel for getting the gradients in the x. And this is our kernel here for getting the gradients in the y. And then you're gonna add the responses. So we have 2 frames, right? Or like two consecutive frames. So we're gonna convolve the first, we're gonna convolve the second, and then we're going to add the responses from the 2. And this will give us the final fx. So fx here is gonna just be applying this to the first image, like let's call it I1, plus fx I2, and similarly on the y as well. Now, if I want to do the temporal gradients, yeah, we have covered that part already. And I have already showed you how to do the convolution, so no need to go through that again. Now, if I want to do the temporal gradients, so the temporal gradients, from its name, we're doing rate of change across the temporal dimension. So if I have, this is the first image, this is, sorry, if I have some first image and I1, and I have second image I2, I want to be able to capture the change across the 2 frames. So you can either do, this one will take the -1, and this one will take 1, or do the reverse. It's always forward or backward, right? Like at the end, these are approximating finite differences, by the way. So it depends, but it will affect it will affect the direction of your u and v, like optical flow vectors. So you will have to somehow do some post-processing to show the final correct uv. But at the end, we're trying to capture in the gradients, we're trying to capture the change. So we can do that change averaged over this 2x2 patch. So that's why we have this kernel. So this is all -1 when it's multiplied. So when I have this kernel here with all -1, it will be averaging across a 2x2 patch. And the on I2, it will be the same. So all of these will be 1, 1, 1. And then when you add together both, what will happen is that whatever is averaged in this 2x2 patch will get differenced from this average 2x2 patch here, which is what we're trying to do as the temporal gradients. Okay. So yeah, I mean, this is the FT. We have the FX, FY, FT. We have everything we need. So we can proceed with simply computing the final UV flow vectors. Okay, let me just make sure first, anyone has any issue with how we computed these gradients? Any questions? Everything is good? Okay, so I'll proceed from here. Okay, so I'll discuss a problem. Lucas Carrata is actually very it's very sensitive, and it usually produces erroneous flow vectors. One problem that it faces that we're going to discuss how to solve is if you are having large motion. So if you're so let's see here, I go from this square has moved to the right, but within a small motion. So what happened is that this, if I'm trying to compute optical flow and I used a window that is still capturing this motion, it will be able to solve the flow vector at the end, because you will be able at least to some of these pixels within the window size that we have selected for our motion. We'll still be able to see this this motion, especially with focus on the corner, that will ensure that any reduced ambiguity in the motion. Now, what happens if you have large motion? Large motion to the extent that even your window size doesn't cover it. So it moves very fast to the extent that from one frame to another frame, what is captured is quite like a significant, like some considerable jump. So this large motion is harder to capture with the normal means for Lucas Canada. So what do you think? What can I do? A very simple mechanism that I can use to help me address this large motion problem. What do you think I can do? Like the brute force way to do it, which is not the optimum, but I mean, I want you to think with me. Well, you have now a problem where an object moved in with the large displacement to the extent that even your your kernel window doesn't cover it anymore. Your window size doesn't cover it. So what do you think? What would you do? First, do you understand that? So the window size is, so remember when we took 3x3 kernel window, 3x3 window size, sorry, for the optical flow in order to have multiple equations for this local smoothness. So this is what I mean by the window size. So now my motion is more than what you have for your window size. What would be the most intuitive thing to do? Someone typed in the chat. Let me see. So Daniel, increasing the window size makes sense. Thank you, Daniel. This is definitely the most the most intuitive thing to do. You can just increase the window size, get more pixels, so that even if it moves larger with larger motion, we can take into we can still be able to have these pixels into account. But then the problem is, however, with increased window size, you are going to probably violate the smoothness constraint, right? Like you imagine now in a real world scenario where you have an arm moving and a human with an arm moving, and it's quite like you see this type of complex motion. If you try to have a bigger window size, there is no guarantee that the smoothness constraint, the local smoothness constraint will hold at this large window sizes. And then it becomes a problem. Like it might end up corrupting your optical flow even more. So that's not, while it is the most intuitive thing to do, but that's not the best. So I'll give you what is the best, but again, thanks Daniel for coming up with the most intuitive one. So usually people who use Lucas Canada use the pyramidal version. So the pyramidal version, what it's meant for, even if you have large motion, it will still be able to capture it, because how it goes, how it is done. First, you build this something called a Gaussian pyramid, and you do this Gaussian pyramid over for the image. This Gaussian pyramid has multiple scales for your image. So this multiple scales can help you. So at this at the coarser scales, sorry, you might be able to capture this large motion already, because you have a smaller scale. And then you use that iteratively to refine until you reach your finest scale. And this is quite important, because at the finest scale, you can still refine. So even if here we had, so remember with the large window size, if you just increase the window size, then the smoothness constraint might not hold. But here, because you're refining with each scale, up till you reach to the final scale, you avoid this problem. So you will be able to refine, but then still have an initial good start from your chorus scale. And this is, again, I'm giving you just the intuitive idea. We'll go a little bit in detail through it. But yeah, I mean, let me make sure first, do you understand the motivation behind going through for the pyramidal Lucas Canada to have this Gaussian pyramid where we have multiple scales, and I'll explain how to build the Gaussian pyramid. But yeah, I mean, whatever we had as large motion, after you downsize to a smaller scale for I1 and I2, will become small motion at this scale, at this chorus scale. So your Lucas Canada will be able to capture it and use it to initialize for the finest scales as you move downward. Okay, does it make sense? Everything is good? Okay, if anyone has any questions, okay, I see something in the chat. No? Oh, okay, I think that was just the early message. Okay, so if no questions, I'll proceed then with how to build actually the Gaussian pyramid. So in order to build the Gaussian pyramid, what we're trying to do, we're trying to go from one scale to another. So with one scale to another, it's two things. First, it is downsampled, meaning it is like you go from high resolution and then you keep reducing, like downsizing your image. But the other thing as well is that you start reducing the details in the image. So a scale is indicative of both the resolution and also like the type of details. So here, for example, you have higher, like this is the finest resolution, you have higher details. You can see, like identify you see here, especially at the hair of the bear, like these type of details and texture is only will be mostly visible at the finest scale. But then the coarser scale just gives you kind of a boundary of give you an idea of what is happening. So as you go here from the fine to the coarse scale, you start losing details. And just it's kind of like maintaining only, doing some form of a low pass filtering. So it's maintaining only the as you go further, it's like the low frequency components. If you feel this is confusing for you, ignore. Just intuitively, you reduce the detail. So as you go here, details gets reduced. So if you, for example, like here, go to the hair of the bear, here you don't see these details anymore. So this is by simply applying, by doing Gaussian convolution. We know that Gaussian convolution is doing some smoothing. We have discussed that before. So it makes sense. It makes the image this is a sharp image. This is a blurred image. So it gets the image to become blurry as you go from one scale to another, and each time you convolve with a Gaussian kernel. But again, this is not the only thing in the scale. You also downsample. So each time you downsample, reduce the size by half and another half, and so on. So this is what it means to have a Gaussian pyramid. So you can simply implement this at once by simply doing strided convolution. We talked about how a strided convolution can, like if you have a stride 2, that automatically will downsize your image by half. And we're doing this convolution with a Gaussian kernel. So it reduces the size and blurs the image. So reduces the amount of detail in it. So this is scale 1, scale 2, scale 3, and this is your pyramid. So whatever was here considered as large motion, let's say, like if the let's assume that there was this type of motion here. Here you will see that it gets reduced quite a lot. So this is what we call coarse because it doesn't have the fine details, while here is the fine scale. So this is the finest scale, this is the coarsest scale. Okay. Any any questions? Yeah, Nurhan. Sorry, what is the point of reducing the details? So with reducing the details, you also get the chance to reduce any and get rid of any noise. It's like, again, intuitively, it has some relations to signal processing, but I don't want to go through that because it might not be as intuitive. But intuitively, you're trying to get a view of what is in the image, but regardless of the details, and use that to type on the initial motion that you're going to estimate, and it's only for initialization. So this is not the final result. And then you use that after you get it, you use that to initialize the motion estimation algorithm on this scale, and then use that and refine again until you come to the finest. So the finest scale has all the details. For example, let's say there is air and like wind, and let's assume that the hair here is long. So like it moves with the air. So you might be able to capture these kind of refined flow at the finest scale. Of course, anyway, Lucas Canada is it's the easiest, but it's the like the most erroneous way to compute optical flow. Like the learning-based ones now are much better, but it's important to understand these classical approaches, and we'll see this actually idea of going through from coarse to fine and doing this refinement is actually implemented in, I remember, in one of the deep learning-based ones as well, just implemented differently. But yeah, does it make sense now, Nurhan? Okay. Okay, no worries. Good. So now that we understand how to build the Gaussian pyramid, and we understand that this is the coarsest scale, this is the finest scale, and we understand what scale is indicative of. So it's not just the downsampled resolution, it's also less details. We can proceed with doing iterative refinement. So in the iterative refinement, what happens is that we have our Lucas Canada, we implement it on the coarsest scale, and then so let me I can give you here. So you compute UV with your least squares, and then you warp IT -1 toward IT using this UV. And we talked about warping before, right? So here we're just doing a translation, except per like it's a dense, like you have for each pixel. So this UV, what do you expect, by the way, the shape of UV? If we're doing it, we're doing dense, let's say, assume we're doing now dense optical flow. So I have IT -1 and IT, this is width by height, this is width by height. So the U and the V, what do you expect will be their size? It's a very simple question, so no, don't overthink it. What do you think? We're doing dense. So what do you expect the output from U and V will look like? Any suggestions? You can type on the chat. No need to. So for each, I am trying to estimate by, when I say that's optical flow, I mean that for each pixel here, you're trying to see how it moved in the, like this is an I2, this is an I1. So U is the motion X direction, V is the motion in the Y direction for your optical flow vector. So what do you think would be the size of U after you compute it? Just in the initial one. Any suggestions? What do you think? Let me ask you in another way. Okay. Do you think that this U and V will just be one vector for the whole image? I try to interact with me. I know you might be shy, but it's okay. I mean, it's okay if it's no need to be shy. It's an informal mentoring session, and we're just discussing together. So this U, what do you think? Is it just one vector, or we actually have it dense throughout the full image? Exactly, Daniel. Thank you. So it will be the size, exactly. So it should be a matrix, and it should be the size of the original image for both. So we have U is like width by height, and V is width by height. Now, at the coarser scale, let's see, this is called C. We will have an initial output here, and we can use it to warp. So we have this W, like the W by H sub C means that this is at the coarser scale. You can use this UV to warp the I1 to move towards I2. So think of it as an initialization, but then you can like go to the like after doing this warping, you can use it, upsample, go to the next scale, and repeat, and then compute the UV with least square, but now on the next scale. I'm not going to talk in details about how to do that. Like you, actually, I think you upsample the UV and then apply it on the next scale and so on. So it's just an initialization for the next scale. Like think of it this way. You're trying to have an initial estimation, UV, that you can use for the next scale. And then in the next scale, you're going to refine. Why this is called refinement? Because you have, remember from how the Gaussian pyramid was built, at the finest scale, you have more details. It's a higher resolution. So, it's less blurry, right? Like it's sharper. So it has more details preserved. So each time you go to a higher scale, you are refining your flow vector estimates. Okay, so this is like kind of in a summary how you would do refinement. And again, I just give you a very basic way of doing the Lucas Canada and a very basic way of doing this. Actually, even the iterative refinement. So the thing is, I don't want to go through a lot of details, but you can see here, you can do an iterative LK per scale. I'm not gonna go through these details, but I just want to make sure that you do understand that like how to compute the very basic Lucas Canada between two images, and that's what we're gonna do even in the practical. And we're not going to do a pyramidal version of it, but just the idea as well of doing this chorus to find that coarser scales can capture larger motion and can use to initialize in the finer scales and so on. Okay. Any questions regarding the pyramidal Lucas Canada? Just the intuitive idea of pyramidal Lucas Canada. The details of Lucas Canada we will cover in the practical anyway with the code. But the pyramidal version, we're not going to go through details. Okay. Okay. So I'll leave it at this. And before we go through the learning based, so this section is actually to motivate you about optical flow. It's used in a lot of video understanding methods, like specifically action recognition, video object segmentation. There is a lot of methods that rely on optical flow input. So that's why it's important to understand the composite. But before that, I think it's best we go through the practical together. Sorry, let's do this version. So yeah, I mean, this so this version of the code, I think you should be able to have it. Let me just confirm it's on Slack. Yeah, okay. So I like if you can download this Colab, and then we can walk through. So I'll walk through you how to like this implementation of Lucas Canada. So what we're trying to do first, if you remember, let's go to the slides even just to keep it. Where? There was a summary. Yes. Okay. So we need, if you remember, this is the summary for optical for Lucas Canada. We need to get the image gradients, x, y, and temporal. So this is the function that will help us to get the fx, fy, ft. This is the gradients we need. And then this is the Lucas Canada part. So remember here, compute UV. We're gonna compute UV per pixel based on this equation. So here, because of we agreed that we're doing the local smoothness constraint, so we always use like we take some window size. So we have for our window size, for each pixel centered around this window, we are taking the patch for the gradients in the x, gradients in the y, temporal gradients within the small patch. This is, remember the 9x2, where like when I started here, I was showing you we're computing it on a 9x2, like 9 pixels. So this by 2, which is the x and the y gradients. So this is here, we're going to construct it. So this is the 9 entries. If we're gonna have a window size of 3, this is 9 entries here, 9 entries here, and so on. This implementation is definitely not the best, by the way. For example, I'm not handling properly the borders. I didn't have the time. Like I just prepared the practical in this morning. So it's yeah, it's a very simple basic implementation. Not everything is covered, but it's fine. We're trying just to understand how to do it. So what I want you is to implement the kernels that can get you the X, Y, T gradients. And at the same time, implement the part that you're going to compute UV. So remember, we are using the normal equation. So we have A transpose A inverse multiplied by A transpose B. And A is based on the IX, IY. B is negative IT. So yeah, I just want you to implement it yourself. And see, of course, and then this part is the plotting. So there is a function called quiver, which is designed to plot arrows, like for the direction of the flow. And I'm giving you here a very, very simple playground. So I have a black image with a white square. And you see, this is it's a very, I think it's a 3x3, yeah, 3x3 square. And it moves horizontally. Sorry, this one moves horizontally. Yes, it moves horizontally. We're gonna play around, like I'm gonna show you. And you should be able to compute the flow vector. You see the arrows here, direction. Ignore this erroneous pixel, but you see that the direction is telling us that the pixel, the square, sorry, is moving, like these pixels are moving in the X direction. So this is what the quiver, like the arrows are denoting. So yeah, let's start here. What I will gonna do, I will leave you, you see now it's 11:48. So I'll leave you till 12. Okay, so I'll leave you 10 minutes. Just look into the code, get familiar with it. We're gonna code this together, so I can do that. So like hopefully to reduce any confusion, we can write the code together. And yeah, so in 12 by in 10 minutes, we can continue the discussion. Thank you. I'm just checking in. If anyone is having issue with getting the images, just text me on the chat. Or if you have issue with understanding any parts, and I'll be monitoring within this 10 minutes. Thank you. Hello, Loyan. Thank you for your question. Actually, yeah, that's a good question. So let me wait. I just need an empty slide. Let me just explain somewhere. Okay. So here, let's say I have my image here, and I'm trying to take a 3x3 kernel. So let me change the color. Things easier. Okay. So I want to take this 3x3 kernel. Oops, sorry. This 3x3 kernel here, which is centered on this pixel. So what will happen is that you see it's half the window size, half the window size. So from what, this is my pixel location. This is the ij that I'm trying to compute its u, and the I and its v. So for each pixel, I want to first get a local window. So this is 9 pixels. So I will take from its location, take the whatever the window size over 2 till I plus size over 2, and j minus size over 2 till j plus size over 2. Okay, where s here is the size, the window size. Does it make sense, Maya? Yeah, I mean, you can type in the chat. Is this better, or do you still confused?
Sorry, I didn't unmute my mic.
No, it's okay. No worries. Yeah, let me know.
So I wanted to understand, is it like plus, it's like a plus, I want to say plus or minus a half.
Exactly. Yeah, because we're trying, so you see here, if you do size like 3/2, like it will, after approximation, it will just be 1. So it will be from I minus 1 till I plus 1. So it will be this is here, and j minus 1 till j plus 1. This is for the y. So then you'll be able to access from your image this 3x3.
That makes sense now. Thank you so much.
No worries, no worries. Good. As I just mentioned, the code though isn't meant to handle boundaries properly. That's it's wrong actually. Like I should be handling the borders, but I'm not. And it's okay. Like we again, like we don't want to overwhelm with too many details that are unnecessary really for now. We're just trying to understand how to compute like the very basic implementation of Lucas Canada. But thanks for your question. And yeah, let me check if anyone else. I think we can actually start the discussion on like the implementation together. So yeah, let me make sure first. Do you all see my like the font, or do you want me to increase it? Is it visible? Any issues? Okay. If no one like if there is no issue, I'll just proceed with that. So at the end, what we're trying to do, we're trying to estimate kernel X. So what do you think I should do for kernel X? What do you think here? So the kernel that I can use to convolve my image. So sorry, my image here. So the kernel that I'm going to use to convolve the image to get the image gradients. And remember, I do it on the first image plus the second image. So I always do it on both images and then sum the responses. So what do you think? Mm-hmm. Exactly. So you have -1 and 1. Good. And kernel Y, what do you think? Thank you, Amos. So what do you think about kernel Y? So kernel Y, this is here, the kernel responsible for the X direction. Remember, it's the rate of change. So I'm trying to take this pixel, like this pixel minus the one before me, or the reverse, it doesn't matter, as long as, again, you process the output correctly. That's all. So yeah, we have that part, and this is averaged over a 2x2 patch. We can do something similar here in the kernel Y, just we're doing rate of change across along the Y direction. So what should I do? Again, you can type. Don't be shy. I'm actually wondering why. Let's see. So Grace, Memdiara, Yuri, Loyan, Daniel, and Omar already guessed one. So what do you think? We are trying to get the rate of change along the Y direction. Which kernel can I use? This is the one I used for the X direction. So I'm trying to get the difference in the X. So if I want to do the difference along the Y, you can type in the chat what do you think I can use. Yes, Daniel, thank you. Exactly. So -1, -1, 1, 1. Okay, that's good. Now for the temporal gradient. Now for the temporal gradient, just to be clear how it's implemented here, whatever we're gonna use for the temporal gradient, we're going to use it to convolve the first image, and then we'll use its negative to convolve the second image. So what do you think kernel T would be? So again, temporal gradient, we're always trying to look the rate of change on the temporal direction. So whatever is happening in image 1 minus whatever is happening in image 2, averaged over a certain patch. So what do you think simply will be the answer here? Taking into consideration this implementation, I mean. So normally, I would say this is the kernel for I1. I should just have 1, 1. Wait, sorry. Exactly, yeah, exactly. So thank you, Omar. So this is the kernel for 1. Yeah, I think we cannot copy in, I don't know why Zoom did that. And this is the kernel for image 2, right? That it's -1, -1, and -1, -1. Now, the fact that I am already just using the same kernel, so I can just take this, multiply it by -1, as we're doing here. So this will be sufficient. So this is here for the X, for the Y, and for the T. And this should be like we're done with computing the derivatives. Now, for the Lucas Canada part, like the algorithm itself, so we go here, we have our window size. We did have the window, and Loyan already were discussing why we are computing this part, just because we need for the local smoothness constraint, we need our window to be centered on the pixel that we're computing its flow. And we initialized our U and V to be the same. We discussed like it will be equal to the shape of the original image, right? Nothing changes here. So this is UV. And then actually it doesn't matter. Like we're always assuming that image 1 and image 2 have the same shape. Otherwise you will have to resize from one image to ensure it's similar to the other. And also one thing, by the way, we have never talked about the colors. So I always assumed that we're always working with grayscale, right? So if image 1 is a colored image, we will need to make sure first that it is converted to grayscale. So all of these here, like the image 1 and image 2 are image 1 and image 2 are grayscale images. We can use it to compute the derivatives, and then we have fx, fy, ft, and we have the uv all initialized to 0. And then we're gonna go So here, as I mentioned, we're ignoring the borders and starting from half window till the image one dot shape of 0 minus half window. Similarly here, you can do padding. So I mean, normally it's very similar to what we do in the convolution. Like if you have borders, you can actually do padding, or like handle it in some way. And then we compute our like ix, iy, it for the, let's say, window size 3 by 3. So we have 9 entries each in ix, iy, it. So this is just accessing the original like fx, fy, ft. So fx, let's be clear that fx, this is the image gradient, right? So it is width by height as well. And same for fy, width by height. Same for ft, it's width by height. So this is capturing the change per pixel in a dense way, like throughout the full image. So now we're just accessing the local window. And then we're taking these, we want to be able to compute UV, the U and the V for this specific pixel. So remember, UV is also, so the U is also width by height, and the V is also width by height. One small thing though, for OpenCV, yeah, if I remember correctly, yeah, for OpenCV image 1 and image 2, it's actually height by width. So whatever we're going to introduce change in the first dimension, this is along the y. In the other dimension, the second dimension, sorry, it becomes along the x. But anyway, like now I have u, I want to be able to compute uv. So first, I can actually set a. So I can make sure that a is ix, iy. So let's see, what do you expect would be the shape of this one? Not sure if I can. Let's see. I want to just show you like a debug here. I think I can just do here import PDB. I think so, but I'm not sure. I think it's IPDB. Yeah, because I usually don't use Colab when I'm really coding. It's only for exercises. But yeah, I mean, I want to show you like how when we're writing, like how the shapes will evolve. Let's actually try to run that. Yeah, exactly. Now we have, this is the dummy, the toy data. Module not found, IPTV, no module, oh yeah. Just import, but I imported IPTV. You know what? I think PTV even will work. I'm almost sure I used to do that directly. We shouldn't have an issue. Yes, exactly. Yeah. So here, if I want to see the ix.shape, exactly. Now we find the 9 pixels, iy.shape. We find the 9 pixels. If I do, so this is, remember here, the 9 by 2. So this becomes the 9 by 2. I mean, we can do a transpose for it though. Yeah, this is actually something we need to account for. Let me see. Yes, we need to account for, so we need to do a transpose, so it becomes 9 by 2. So this is the remember here, I just want to make sure that you're following. So remember here, yes, remember here in this equation, we had this A was this 9 by 2 matrix, and then we ended up, we ended up doing here A transpose A inverse and then A transpose B. So this is what we're going to do. So we have here this 9x2 matrix now. So we have constructed it together. So anyone has any issue with how we have constructed the A? So what do you think I should do next? So if I wanna, if I wanna do this, let me go walk through you it. So we're gonna have MP transpose A. Actually, I think it's just A dot T, if I remember correctly, right? Let's see. There's something called A dot T. Yes. Yeah, exactly. It's just easier. So we're gonna do A transpose A multiplied by A, and then do pseudo inverse. So there is a linear algebra module inside the NumPy, which has the P-inf exactly, and this one. So this part here, this is this part. So let's call it, this is the pseudo inf. So this pseudo inf is just computing this part here. Let's actually make it here. So what do you think? This pseudo inf, what is the shape of this? What do you think? We were just discussing it. We talked about how it, you can compute it directly, by the way. You don't have to do this dot product. You can compute it directly. And that's what we did even in the slides. But what do you think? So this A transpose A, what do you think is the shape? Any suggestions? Okay, I can just show you. Yes, Daniel, exactly. It will be a 2x2. So here we talked about, so this 2x2 matrix, this is the A transpose A. You can compute it directly, but just summing, like multiply the fx by fx itself and sum and so on. So either do this or this, both. It's exactly the same. And then we so if we're all agree, so I can just show you anyway. We can always good to do confirmation. We're proceeding in the right direction. So the pseudo inf dot shape. So yes, we have our 2x2 matrix. Now the next part is the A transpose B. So the A transpose B, let me just write it here so we don't forget. What we're trying to do, let's call it ATB. This is gonna be A dot T multiplied by B, which is negative IT. So this is going to be your A transpose B. Again, what do you expect? This will, like the size of this one? So let's go through this. A transpose is 2x9. And then this one should be 9x1, right? So you end up with just a vector 2x1. So this should be ATB. I'm not sure. I might need to do a reshape of that vector. Let me see if it works. Not sure. So ATB dot shape. Oh, if there is no error, yeah, exactly. So it becomes 2. So this is our 2x1 vector. And now the remaining part. So what should I put for Uij? The final thing. Now I have my pseudo inverse, and now I have my ATB. It's very simple. I should just multiply both. Pseudo inf and ATB. Okay. Oh, sorry. Of course not. So this is gonna be, let's say, call it U vector. So what do you think would be the size of this U vector? What do you think this would be equal to? So I have a 2 by 2 multiplied by 2 by 1. So what do you think U will be equal to? So 2 by 2, and then multiplied by 2 by 1. So this is just going to be 2 by 1 vector, right? And then this is what, so U of 0 is going to be the real, like the U component of the optical flow. And the capital U1 is the V component of the optical flow. And all of these for a single location, of course, the IJ, because that's what we started from. Like this is where the local window was centered around, right? So this is, yeah, this should be sufficient. Let me make sure. Everything is correct this time. Yeah, exactly. So yeah, you see here what I was actually plotting. So I had this square, like 3 by 3 square, a white square on black background, and it was starting at pixel 1, ending at pixel 3 in the X and the Y. Now, sorry, this is okay. This is height width. So this is a height, like everything here is always height by width. So this is accessing here, this dimension, and this is this part is accessing the X dimension. So if I want to move it along the X, I will simply move it. I want to move it 1 pixel. So now it will start at 2 and at 4. Instead of starting at 1, it starts at 2. So you see here, this pixel here, this square, sorry, moved in the X direction by 1 pixel. And that's what we see here. Like we see these arrows giving us the direction that it is moving in the X direction. I'm honestly not sure why this is. It could be like a minor bug, or it could be related to the window, how it's constructed. I don't remember, honestly. Again, I did this toy example very quickly in the morning, but the whole idea is just to, again, to show the implementation of Lucas Canada, and we do it together. Let's say I want to move on the Y. So this means I'm going to move here. I'm moving on the Y direction. So this moving like that with 1 pixel. Okay. So it should, the arrows should reflect the motion. Let's see, it's upward. It's probably flipped kernel here. As I mentioned, it doesn't matter. Like the gradients, by the definition of the gradients, it's like you could approximate it with forward, backward, centered difference. As long as you just make sure that you're handling the motion, like the real output motion properly for the UV. So here we are moving down with 1 pixel, and so this is frame 1, this is frame 2. And I use these as input to Lucas Canada. So here it is showing that it is moving in the downwards. What if I want to do diagonal? Like if I want to do here 2, 4. So this is moving in both X and Y. So again, it's showing the majority of the pixels properly. I don't remember. This is, it could be part to the, yeah, I mean, it's probably because of the construction of the small, what is it called? The majority of the window, the local window in these pixels might have resulted in these erroneous flow vectors. In addition to the fact that these parts are like an edge. Remember when we were talking about how in the aperture problem it can make an issue. So here on the corner, it was able to capture it. But yeah, I'm not sure exactly in order to do it, like you will have to actually write the numbers literally so that you will able to trace. We have everything here, so you can easily trace it, but I'll leave that to you. It's just, again, a toy example to just show you what Lucas Canada can do. And all of this, we're using like a window size 3. You see, if I use a very large motion, you will start finding weird things happening. So let's say I'm gonna increase everything with 4 pixels, which is actually beyond, beyond our window size. My expectation is gonna be a crappy flow. Exactly, it doesn't make sense anyway. It's outside, right? Like it doesn't make sense at this point. I'm actually not sure even why this specific, like I'll have to, again, you will always have to trace it. And this is again not the complete implementation because I'm not taking the borders properly into account. So we're always starting at this pixel here, the half window. But yeah, anyways, it's just again a toy example. What else? You tell me. What, like first, anyone has any issue with what I showed you so far? With this toy example, like, does it make sense how we implemented it together? Yeah, any questions? You can type or just open the mic. Also, yeah, one thing I think I might have forgot to tell you this one. So this UV flipping, like we're doing here, up, down flipping. This is just simply because when you're computing here UV, you want to make sure that everything is with respect to the origin at the top. So if you take this out, you will find it's like it's plotting the UV in a way that it's like the origin down. So that's not the case when we're working with images. So that's the only reason we're doing this flipping. So yeah, exactly. So it's like we have here 0, 0. But that's not how it works in images. So that's literally why we did this flipping. I think otherwise, hopefully the code is clear. Let me know. Anyone has any issue with this part or this part? Things are good. Okay, so I'm assuming with this silence, I'm assuming that everyone is happy with the code, like things are clear. Okay, I'll try. Anyone actually was able to fully implement it within this 10 minutes, or like at least get the derivatives within this 10 minutes? Or did you find it hard? Or you found like my explanation was kind of not related to the code? Don't be shy. Again, you can just open the mic and comment. It's okay. Yeah, I mean, yeah, let me know. Is it clear or you found the things, yeah, you felt disoriented, like it was not related to the lecture? Omar, I couldn't make the inverse first time to hear about p-inv. Okay, no worries, Omar. It's okay. I mean, we're learning together. Yeah, it's part of the linear algebra package in NumPy. So you don't have to know the details. And no worries, Grace, of course, it's okay. I hope you will find it useful. You can always check the recording afterwards and implement it yourself. And if you find any issue, you can check the recording and let me know also. But yeah, happy that we were able to fully cover like a motion estimation as well, and did a small toy example. And this is even if you want to see with frames, like a real image. Let's see. I'm assuming that I don't have the images yet. Exactly. So I can show you here. If we read these two images, of course, we're always working grayscale. That's why you see it visualized like that. And then compute the Lucas Canada, and then I'm plotting here every 10 pixels in the X and the Y, and plotting the arrows so we can see. But let me actually show you that video so you understand what is the what's the motion. Let's see here. So you see here, if I like how this is moving. So first there is camera motion. Like let me just again roll back. So this is frame 1. There is some camera motion happening, and then there is the bear also moving, right? So first, what do you think would be the correct flow vector direction for the full image? Forget the bear now. So remember the camera, like I'm gonna get back again to frame 1. The camera is moving in the left to the left. So what do you think the flow vectors will look like for everything else beyond the beside the bear? So the flow vector, we're trying to estimate the apparent motion from one frame to another. What do you think apparently that the motion will be? And when I say apparent, there is exactly, Omar, thank you. It appears to be moving to the right. The camera is moving left. So as I'm moving left, panning left, everything else seems as if it is moving to the right. Although it's not actually moving, but this is again, yeah, it's actually the reverse direction, Grace. So the reverse direction of the motion of the camera. So if the camera is panning to the left, everything else seems as if it is moving. So you see here, look to this leaf, like this. Let me actually make it bigger. Like if we try to take some point, so take this leaf here, see what is happening as I am, oops, okay. Sorry, I think, yeah, I cannot zoom and move. Oh, weird. What? I don't know why. Oh, that should work. Okay. Yep. Let me just see if I can zoom and show everything. Okay. So you see here, if we took these leaves as a point of reference, as I am moving, okay, yeah, I cannot keep it. As I am moving, you will see that it is as if it is moving to the right, although the camera motion is to the left. So it will be the reverse. So this is exactly what you will see here. Of course, again, as we talked about, Lucas Canada is quite erroneous. So you will things are not going to be perfect. But there is most of the flow vectors, you'll see that it is kind of telling us that it is moving to the right direction, except the part for the bear. So the bear, you see that it was like the muscles of the feet and the legs. This is just getting us how it was moving. So it was moving downward and to the left. So this is the part that is related to the front part of the bear. So yeah, this is again another example. Like I hope this is yeah. Let me know if anyone has any questions. I hope this was a good tutorial to walk through you the motion estimation part. Yeah, let me know if you have any questions you wanna. Yeah. If no questions, the last part is just the learning based, and I'll finish it in a very quick manner. So it's just again to I'll be brushing over some of the methods that learn flow instead of just computing it in an analytical way. So Lucas Canada is an analytical approach, but there are ways that you can just learn optical flow, and it turns out to be faster in inference. It turns out to be also more it becomes better actually, especially with like this kind of large scale data. So the first method that appeared learning based optical flow was FlowNet, and with FlowNet they used actually synthetic data, and especially for optical flow, you will find that this kind of synthetic data was already useful enough to teach the model how to correlate between two frames and compute and estimate the motion from between these two consecutive frames, and then you are able to use it to a good extent on any real video you have. So it started with FlowNet, which was a very simple architecture, taking 2 input frames and then computing the correlation tensors between these 2. So we have input like output features from frame 1, output features from frame 2. You can compute the correlation. So how this pixel, 1 pixel here, relates to a local window in the other image, and so on. And you can take this correlation tensor and parse it like through multiple convolutions until you're able to do the final prediction of the optical flow. I'm not going to go through the details, no need. I'm just introducing to you. FlowNet 2.0 started to do real 3D motion instead of just simple 2D motion, which was like simple. Remember, we talked about affine is just simple, like it can include non-isotropic scaling, but it's very simple, like within the same plane, you're changing, doing like shearing, stretching, and translation, rotation, all of these. But they introduced this real 3D motion in the dataset to capture better like a training for the optical flow. And yeah, we can't skip that part, but yeah, they did have different ways of scheduling, like which data set to train on first. Like they started with the simple one and then the more complex one with the 3D motion. They also had the flow refinement. So remember how iterative Lucas Canada, actually iterative Lucas Canada, again, you can run per scale and then use it to initialize the next scale. So they had this way as well, but where they estimate an initial flow, use the flow to warp the image and get a warped image in addition to image 1 to go for another network. So you can use it to capture large displacements and then refine with the small displacement. So large displacement, it's better to work on like coarser images, but then you can refine with on the finest resolution with the small displacement. I don't remember if they were using different scales or not. This is something I gotta admit I'm not sure of. But just the idea that they separated large displacement from small displacement and captured the large displacement first, use it to initialize, and then use it later to and use a specific network to refine the small displacement one, and then fused between both. So yeah, this type of refinement and warping the image to be input for the next stage, this iterative way, this is how iterative, like it's inspired by iterative Lucas Canada at the end. Yeah, yeah, I think that's it. I mean, you will find also a lot more optical flow methods like Raft. I can show you. So there is very popular paper on action recognition from Simonian and Zisserman. This was the first 2-stream approach that was relying on action recognition. Oh, I'm not sure why this is on Europe's 2024, but it's definitely not Europe's. Ah, okay, exactly. So yeah, it's so this paper was in back in 2014. So what they were trying to do, they were trying to have a stream that is processing like the visual information, and then another stream processing the temporal information in terms of multi-frame optical flow. This is how they were doing action recognition. There is a trend in video understanding to avoid computing explicit optical flow, but it's still like I think it is still relevant to understand these. There is a lot of video object segmentation methods up till now. So for example, MATNet, just like motion attentive segmentation. There is actually things even in CVPR last year. Just forgot their names, but there are a couple of video object segmentation methods that, especially the automatic ones, that try to use optical flow as input, even within the attention-based mechanisms. It's a very strong signal for the motion. So, and you can capture boundaries very well with it to an extent at least. So yeah, I mean it's something important in various like methods that are processing videos generally. So yeah, I'll stop here and yeah, take any questions, or if you have comments, if you feel something is like missing from the tutorial, you can let us know also to help us get better. Yeah. Okay, so I'm assuming no questions, so everyone is good. Thanks for coming, everyone. Just stop the recording.